Hello friends, I welcome you in lecture number 28 on hypothesis testing. In this lecture, we will discuss one more question on F ratio test for the equality of two population variances. This question was asked in GTU Summer 2022 exam. The question is, two random samples are drawn from two populations and the following results were obtained. So here we are given the observations for sample 1 and sample 2. In sample 1 we have 1, 2, 3, 4 and 5 observations. Therefore sample size is n1 equal to 5 for sample 1. In sample 2 we have 1, 2, 3, 4, 5 and 6 observations. So sample size for sample 2 is n2 equal to 6. And suppose the variable for sample 1 is denoted by capital X and suppose variable for sample 2 is denoted by capital Y. Now the question is, find the variances of the two samples and test whether the two populations have the same variances, and consider significance level alpha equal to 0.05 or 5% level of significance. Here we are not given sample variances, but we are given the observations of sample 1 and sample 2. So using this data for sample 1 and sample 2, first we have to find the sample variances, and using those sample variances we have to test the hypothesis that two population variances denoted by sigma 1 square and sigma 2 square are equal. So this is going to be our null hypothesis, and the alternative hypothesis is that they are not equal, that is two populations have unequal variances. Now here, because we are interested in testing the hypothesis that two population variances are equal, we have to apply F ratio test for the equality of two variances. But to apply F ratio test, we must be sure that these two conditions are satisfied. First condition is that two populations must follow normal distribution. The underlying populations must be normal, and second condition is samples must be independent. So here no condition is given. They should specify that two populations are normal and they are independent also. But if they don't specify, we will assume that both the populations are normal and independent, or we can say that two samples are independent. So if those two conditions are not given in the question, you should assume those two conditions, and then only you will be able to apply F ratio test. Now we recall the formula for sample variance. If x bar is the mean of the number of observations in the sample, and if there are n observations, then the formula for sample variance is sigma x minus x bar whole square divided by n minus 1. That is, we are taking sum of squared deviations from arithmetic mean, and we are dividing by sample size minus 1. We can also rewrite this formula in this form also. It is given by sigma x square minus n times square of sample mean divided by n minus 1. And this formula is helpful, this shortcut formula is helpful if our x bar is not an integer. So we are going to use this formula to find out sample variances for both the samples, and for that first we have to decide sample mean, and then we have to decide sum of square of x values, and similarly for second sample we have to apply this formula. So first I have obtained sample mean and sample variances for both the samples. For sample 1, first we find out sample mean, that is we have to add all these values and we have to divide by n1 equal to 5. Formula for sample mean is sum of all the observations divided by total number of observations. Here there are 5 observations and we are taking addition of all the observations, and we find that sample mean is 24.6. Now for sample variance we will use this formula. Suppose sample variance for first sample is denoted by S1 square. Then first we find out sum of all these squares of x values. So that is 21 square plus 24 square plus 25 square plus 26 square plus 27 square. That is, I have taken square of all these observations and I am adding them, and I find that sigma x square turns out to be 3047. And now we have all these things which are required to calculate sample variance. We substitute all those things in this formula. Sigma x square is 3047, sample size is 5, n1 is 5, sample mean x bar is 24.6 whole square and divided by 5, that is n1 minus 1, which is 4. And using this formula we find that sample variance for first sample is 5.3. Same thing we do for second sample. We have 6 observations and we use capital Y variable for sample 2. Therefore sample mean is denoted by y bar, and we are adding all these observations in this sample mean, and we are dividing by 6 to write down the sample mean for second sample. So our sample mean for second sample becomes 29, and using this formula we will calculate sample variance. Sigma y square minus n2 times y bar square divided by n2 minus 1. So here we require sigma y square, that is, I have to take square of all these observations and add them. So that I have obtained here, and sigma y square turns out to be 5154. So here I substitute sigma y square. n2 means number of observations are 6, square of y bar, that is 29 square, divided by 6 minus 1, which is 5, and sample variance for second sample turns out to be 21.6. So now we have sample variances for both the samples, and we assume that two populations are normal and independent also. Therefore we can apply F ratio test, and we assume that null hypothesis is true, and under this assumption our test statistic for this hypothesis test is ratio of sample variances that follows an F distribution with numerator degrees of freedom equal to n1 minus 1 and denominator degrees of freedom equal to n2 minus 1. And before that I have to write all these things. I am taking these two assumptions, that two populations are normal, the samples are independent, or we can write that populations are independent. Null hypothesis is that two populations have same variances, and alternative hypothesis is opposite of this statement, that is sigma 1 square and sigma 2 square are not equal. And because we have this not equal sign, it is a two-tailed hypothesis test, and we are assuming that null hypothesis is true, and we are testing this null hypothesis using F test, and the level of significance is given as 5%. And now I have calculated test statistic. Capital F is S1 square over S2 square. We have obtained S1 square as 5.3, S2 square is 21.6, and this ratio turns out to be 0.24537, and if we round off up to 2 decimal places, it is 0.24. And the next step is to decide the critical values. Now because we have two-tailed test, we have to consider the area in left as well as right tail. So we have to divide this alpha 0.05 by 2, and we will consider that we have 0.025 area in both the tails. Suppose this area is 0.025 and this point is denoted by f suffix 0.025 because area to the left side of this point is 0.025. On horizontal axis we are considering values of f distribution, and area in this left tail is also 0.025, and this point is that point such that area to the right side of this point is known to us. So here area to the left side of this point is 0.025, therefore area to the right side of this point is 1 minus area to the left side of that point, because total area under probability density curve is always 1, and this turns out to be 0.975. Therefore this critical value is denoted by 0.975, and using f distribution table we have to determine these two critical points, and these two regions are rejection regions. Here this region and this region both are rejection regions, and the region between these 2 points is non-rejection region. And here to decide this point we have to look for 2.5%, or we have to look for alpha equal to 0.025 area in the f distribution table. We have different f distribution tables for different levels of significance. So we have to look for f table which is for alpha equal to 0.025 level of significance, and in f table we have values of these critical points for numerator and denominator degrees of freedom. Here degrees of freedom for numerator are first sample size -1, first sample size is of size 5, therefore numerator degrees of freedom for first sample will be 5 minus 4, that is 5 minus 1, that is 4. Second sample is of size 6, therefore denominator degrees of freedom are 5. So we are interested in this critical value f 0.025 with 4 degrees of freedom in the numerator and 5 degrees of freedom in the denominator, and for that I am searching in the f table for alpha equal to 0.025 with 4 and 5 degrees of freedom. This is my f table which is giving us the critical values of the f distribution for alpha equal to 0.025. So this f alpha are in this table, and here we have numerator degrees of freedom equal to 4, denominator degrees of freedom equal to 5, and these column headings are for numerator degrees of freedom. This left column corresponds to denominator degrees of freedom. Here nu1 is 4, so I have to look below this column heading, and nu2 is 5, so I have to look in this row, and for that I am taking intersection of this row with this column, and I will search what is the point of intersection. That is our required critical value. Let me remove this, and you can see the critical value for alpha equal to 0.025 with 4 and 5 degrees of freedom is 7.3879, or we can write up to 2 decimal places as 7.39. So that I have mentioned here, or I can write that this is 7.39. So I have shown all these things here. This is figure for probability curve of F distribution, and here I have written that this critical value for 4 degrees of freedom in the numerator and 5 degrees of freedom in the denominator is 7.39. Now what about this critical value? So we are not having F distribution table for this alpha equal to 0.975. So for that we can use this property, F suffix 1 minus alpha with nu1 and nu2 degrees of freedom can be obtained by taking reciprocal of F suffix alpha by interchanging these 2 degrees of freedom, nu2 comma nu1. And here 0.975 is nothing but 1 minus 0.025. Therefore we have to find out 0.025 critical value for alpha equal to 0.025, but here instead of 4 and 5 we have to write 5 and 4. So that I have written here, critical value for alpha equal to 0.975 for 4 and 5 degrees of freedom. This 0.975 I have rewritten as 1 minus 0.025, and using this property this is going to be 1 divided by F suffix alpha, which is 0.025, and interchange this 4 and 5, which is 5 and 4, and I have to look for F distribution with alpha equal to 0.025 and with numerator and denominator degrees of freedom as 5 and 4. Now I have to search for nu1 equal to 5, that is I have to search below this column, and nu2, that is denominator degrees of freedom are 4, that is I have to take intersection of this row and this column, and I have to write down what is intersecting point. So they are intersecting at this point, and now I am removing these two, and I find that 9.3645. This is F suffix 0.025 with 5, 4 degrees of freedom. This is 9.3645, and up to 2 decimal places we can write this as 9.36. So that we substitute here. Here I have written this value 9.36, and reciprocal of 9.36 is 0.11, and therefore this critical value is 0.11. This critical value is 7.39. Now we compare our test statistic value with these two critical values. If test statistic value is to the right of this or to the left of this, then we are in rejection region and we will reject the null hypothesis. But if calculated value of test statistic is in between these 2 points, then we will be not able to reject the null hypothesis. And here calculated value of test statistic is 0.24, and this is 0.11. So 0.24 might be somewhere here. Suppose this point is calculated value of test statistic 0.24. So you can see we are in non-rejection region. Calculated value of test statistic is greater than 0.11 and less than this 7.39. Therefore we are in non-rejection region, and therefore the conclusion is that we fail to reject null hypothesis. So that I have written here, that this critical value F suffix 0.975 is 0.11, which is less than calculated value of test statistic, and this is less than this critical value, and therefore we are in non-rejection region. Therefore we fail to reject the null hypothesis, and the null hypothesis is that two populations have the same variances. So we can say that there is no evidence to reject that the two populations have the same variance, or we cannot reject this statement that sigma 1 square and sigma 2 square are equal. So this is another example on F ratio test for the equality of variances. We have discussed two examples before this lecture on F ratio test. What is new thing in this problem is that here we are given observations of the sample. We are not given sample variances and arithmetic means or sample means. So to apply F ratio test, we have to first calculate sample variances. So that work is more here as compared to previous lecture work. In previous lecture we were given the sample variances. So sometimes they give the question in this form also. They are writing the observations of the sample which we have taken from two populations, and using sample data first you have to decide sample variances, and then you can apply F ratio test. And be careful, if you are not given these two assumptions in your question, then you should assume that these two conditions are satisfied, then only we can apply F ratio test. So this is all about this lecture. I hope you like it. Thanks for watching.